Hi everyone, welcome to my YouTube channel. Today we will be discussing about infinite square well potential. This is a very famous problem in quantum mechanics where Vx, the potential, is 0 inside the box and infinity everywhere. So outside the region the wave function is 0 because the probability of finding the particle outside this box is 0. We have already seen in the previous lecture that if the potential is time independent, then we can divide the solution of Schrodinger equation into two parts. One part is only dependent on time and the other part depends on position coordinate r. The time independent part of the Schrodinger equation is known as the time independent Schrodinger equation, which is given by minus h car square by 2m d2 phi dx square plus v phi equals to e phi, where E is the total energy of the system. Now in case of infinite potential well, Vx or the potential is 0 inside the well, and so equation 1 becomes minus h car square by 2m d2 psi by dx square equals to e psi. And now taking the minus h car square by 2m part on the right hand side of the equation, we get d2 psi by dx square is equals to minus 2m by h car square into phi, and I am writing k square equals to 2m by h car square, and we know this is a standard equation in mathematical physics, and its solution is a sin kx plus b cos kx, where a and b are constants. As the potential is infinity at the boundary, so the wave function must be 0 at the boundary. Phi 0 is 0, and if we put x equals to 0 in this equation, we get b, so b is 0. So we are left with the solution phi x equals to a sin kx. Now put the condition that phi at a is 0, so a sin k is 0, and we can put a equals to 0 because in that case we get the trivial solution phi x is 0, which is no use of us. So we are writing Ka equals to n pi because we know that sin n pi is 0. So K is n pi by a. So the solution becomes a sin n pi x by a, where n is 1, 2, 3, 4 to infinity. But n equals to 0 is not taken because in that case we will have a trivial solution which is phi equals to 0. This has no use for us, and the negative numbers, that is minus 1, minus 2, these numbers are also not important because they will not give rise to new independent solution. We know that k square is 2me by h car square. Here we are just adding the subscript n to identify the values of k between different solutions, and so En is h car square k square by 2m, and after putting k's value as n pi by a, we get n square pi square h car square by 2m a square. Now normalizing the equation or wave function, so phi square dx 0 to a should be equals to 1 because the wave function outside this range is 0. So after putting the value of phi as a square sin square n pi x by a, we get this equation, and taking out a square of the integration and just multiplying 2 in the numerator and denominator, we get this equation a square by 2 0 to a 1 minus cos 2 n pi x by a, because you can say that 2 sin square theta is 1 minus sin 2 theta. The same equation I am using here, and after integrating it and putting the limit 0 to a, we get a square by 2 into small a. So this is equals to 1. So here we get a equals to root over 2 by a. We are only taking the positive real root of the equation. So the normalized wave function is phi n equals to root over 2 by a sine n by x by a. These are energy eigenstate because they have definite energy, and the energy is given by the equation En is n square pi square h car square by 2m a square, where n is 1, 2, 3. These kind of solutions are only possible because here the potential is not explicitly dependent on time. In fact, it is 0 in this case. N equals to 1 corresponds to ground state, n equals to 2 is first excited state, and so on. From here we can see that the particles can have any kind of energy, that is the energies are quantized. These are some wave functions. This is the ground state, first excited state, and this is the second excited state. This represent how they look like. With respect to the center of the potential, the solutions or the wave functions are successively even and odd. So the ground state is even, the first excited state is odd, and so on. The nth state or wave function has n minus 1 nodes. Nodes means the zero crossing. So in this example we can see that there is no nodes. We don't consider the endpoints, only the point or the zero crossings between the endpoints. In this case we have 1 zero crossing, so it has one node, and if we use the formula n minus 1, so 2 minus 1 is 1, so the formula is also matching with our observation. We know that sinusoidal functions are orthogonal in nature. So is the energy eigenstate, because the energy eigenstate is a sinusoidal function. So phi m star phi n dx integration is delta mn, where delta mn is a delta function, Kronecker delta function, where if its value is 1 if m equals to n and 0 otherwise. As phi n are normalized, so we can say that phi n are orthonormal set. That is, if any function satisfy the boundary condition and the same boundary condition which is present here, and then we can write that function as a linear combination of phi n's. Like say fx is satisfying the same boundary condition, so we can write it as summation of n equals to 1 to infinity cn root over 2 by a sine n pi x by a. So the general solution, we always know that these are the linear combinations of the energy eigenstates. So we can write as summation over n equals to 1 to infinity cn root over 2 by a sine n pi x by a e to the power minus I ent by h cat. The exponential part is the time evolution of the wave function. So that's all for today. Thank you very much for watching this video. If you like my video, please subscribe and share it with your friends. I will see you in the next lecture.